All right, so I told you last class that I was going to identify a 8086 assembler emulator. And so there's kind of a famous one. And so let's go this way for, actually, I'm just going to do a search. So it's called EMU 8086. And I already put links up on the website for this. And this is a microprocessor emulator. So if you are a Windows user, you get easy mode for this. You download this zip, open it, and double click setup. And that will install it. All right, so if you are a Windows user, this will work for you. Now, this is kind of this one's been around since like 2004. I mean, so this has been around for a long time, and it's actually emulating the 8086 processor, which is a much older processor than we have in our computers today. But it's still an Intel architecture. All right. So now with that in mind, and we'll look at some of the registers here in a second, it's really a subset of what our processors today would have. Okay. And if you're trying to see the link, just go to your Blackboard, and I already linked it all in there. I'll talk about to the Mac people here in a second. Let me just make sure this is still cooking back here. Okay, that's fine. All right, so in any case, the 8086 processor was from many years ago, before. So kind of let's go at this route. So in your readings or any of the papers you've worked on, what CPU architectures have you heard of? So I'll kind of get us started. You've heard me mention 8086, right? Then you have the 286 architecture. Then the 386 architecture. You can pick it up from there. What comes after 386, do you suspect? 486, okay. What came after the 486? This one's it's kind of a trick.
X86?
No, kind of a trick question, a little bit of a trick question. Yeah, oh. So it was the 586 architecture, but they named it the Pentium processor. All right, but that was the 586 architecture. 686 architecture was still Pentium line, so on and so forth. So we had Pentiums for a while, right? And then there was a branch. We had a processor called the Celeron. Any of you remember the Celeron processor? Okay. And then you had a company called AMD that started making Intel architecture competitors. So you had one of their famous processors called the AMD Athlon. And then they had the 64-bit Athlon, which we researched in here, right? All right, so that's kind of when AMD went downhill a little bit after that kind of debacle, if you will. And then today, our Intel processors are called what? We had the Core Solo was our first move towards let's call it the latest architecture of Intel, the Core processors. So you had the Core Solo, then you had the Core 2 Duo. And now you have what? Core i3, Core i5, Core i7. Yep. So effectively, you have that's our current rendition, and then you have incremental architecture upgrades. So this computer here is running a Core i7 from 2012. Well, a Core i7 that came out last week, let's say, is going to have an updated infrastructure from this one. Instruction set will likely be the same. Now, when I say instruction set, what does that mean? What does that mean to you? Instruction set. Okay, fair enough. So it's the list of the magic tricks that a CPU knows how to perform. The instruction set from a human being's perspective is going to be the list of commands that we can give that CPU. All right, so the modern Core i7 processor is going to be a superset, at best, of the Core i7 processor that's in my computer here from 4 years ago, 5 years ago, something like that. All right. Why is that? Why are they supersets of each other? because the program we're about to run here, the 8086 emulator, is actually written in 2004. That was a couple of years ago, right? Go ahead. Yeah, backwards compatibility, which is going to work out well for us in our example here. Okay, so let me keep cooking here. So if you're a Mac user and you want to run this 8086, I found that the best equivalent product to the 8086, EMU 8086, is to actually run EMU 8086 on a Mac using a Windows emulator. All right, so we're going to use a program called Wine for the Mac. Have any of you ever used Wine before? It's also on Linux. So that's a, so does anybody know what Wine stands for? I keep calling it Windows emulator, but go ahead. Wine is not an emulator. All right, so Wine is an implementation. Oh, are you impressed?
I couldn't remember it.
Yeah, you're just missing all these things today because you're too busy with his other fluff. Yeah. Yeah, so it stands for Wine is not an emulator. It's an implementation of the Windows executable stack. So you can run Windows applications. Let's say in general you can run relatively simple Windows applications, which the good thing is EMU 8086 is one of those. It does work for some games. If you are a hardcore gamer, you probably don't want to rely on Wine for... Well, it does. There's a version of Wine called WineX.
It's never
That's there's a couple of games that it will work for ish. All right. So in any case, I have a link up there for the Mac people. It's going to take you to a page that looks like this. All right. And so what it's going to have you do is it's going to use a first of all, you need to get Wine installed for the Mac. All right, so this is going to have you use a package manager for the Mac called Brew. If you are on a Linux machine, you likely already have a package manager like apt-get or yum, and you probably know what you're doing already with this. But if you're on a Mac and you want this to work, you need to have about 30 minutes set aside. It's not hard to install. It's just time consuming. You basically copy and paste stuff and then wait while it does its thing. All right, so first thing you need to do is you need to install Xcode. You do that from the App Store. So you come over here to your App Store icon, go and search for Xcode, and you download Xcode. That's about a, let's say, 1.5 gig download, something like that. So that, depending on your internet connection, that might be longer than 30 minutes. But assuming you already have Xcode on your computer, you'll start with Homebrew. So you copy this line, you paste it out here, and you answer the questions it puts on the screen. Basically, you just say Y for yes, and then it cooks. All right, does its thing for a couple minutes. After you've done that, you put in this command, paste it, let it do its thing. It gives you a warning that it might give you this thing where you have to agree to the Xcode license agreement. If it does that, type that in, do the thing, then copy this, let it do its thing. It takes a few minutes, then do this, let it do its thing. It's just installing the prerequisites pieces of software for Wine. All right, this guy will probably take about 8 to 10 minutes. Everything goes pretty quickly up to this point. Now I'm on this step, the brew install Wine. So I just I had it cooking before class here. So the last thing I put in was that guy. All right, so now I'll go ahead and paste that guy in there. So we're asking Brew to go ahead and it'll find Wine, it'll download it, and any prerequisites. So notice that it's not just getting Wine, it's getting all of this crap that is needed by Wine. All right, that's what package managers do for us. They make our life easier so we don't have to go and download each of these things individually and then install them by hand and that kind of stuff. Okay, so we'll let that cook. When I did this on a different computer earlier, this failed about halfway through. So if that ever happens, you just run it again. It's because one of the packages compiled, there was a network timeout, and just if it was halfway through, but was like here, let's say when it failed, when you run this command again, it'll just try to install those guys. So all the other ones it'll already find are there. Okay. And then this is pretty close to the last step. We'll see the other steps throughout class today as we just let this cook. Then we'll actually install the program. So I guess while this is at it, I will go ahead and here's our emulator. I'm going to go ahead and download. This is the same thing that the Windows people downloaded. Difference is that the Windows people were able to just double click on setup. The Mac people need to do all this installation stuff in order to run a Windows program. Okay? But this will be handy for you Mac folks because now you have something that has the potential of running simple Windows applications. So like we kind of talked about, games are probably not going to be really in its wheelhouse, but if you've ever found a little utility or something like that that's Windows only that you wish you can run in your Mac, there's at least a decent chance this will run it. Okay? For utility type things. All right, so we'll let that guy keep cooking. We'll check in on it every now and then as it's moving. You know, it just finished this guy. Now it's going to move on to this guy and so on and so forth. So every few minutes we'll check back on this and see what the current progress is. Okay, but I want to start here. We started talking about this last class. And kind of what I was getting at with the different architectures, we're going to be using an 8086 emulator, which means that we're going to be limited on the number of registers we have access to. Not that limited, but a couple of the examples that we've seen in class have used EAX and EBX and those guys with the E in front of it. Those are 32-bit registers. Well, 8086 is not a 32-bit chip. It's a 16-bit chip. All right, so with that in mind, EAX does not exist in 8086. Just AX does, and the ones beneath that. All right, but as we talked about last class, they're kind of supersets, right? I think I did. It was in here. I showed the picture of EAX, and then AX is like the second half of that, and then AH is the first half of that, and AL is the right half of that. So all of that's true, except EAX doesn't exist. So everything from AX in is all still the same. Okay, and we're going to talk about these things here. So I want us to think about these like our magic tricks or our Legos or our tools. These are the things that we have access to. If we think about our CPU as a pile of resources, these are the things that we have to work with. All right, any problem we solve, we'll solve in terms of these guys. All right, and then we're also going to be looking at a series of YouTube videos that I'll post, but what we'll do is we will look at something in class. Most of the videos are about 2 minutes long, and then we'll see how those work, and he uses the 8086 emulator as well. So those should all give you lots of ways of practicing this stuff. Okay, so our big four registers first, AX, BX, CX, DX. The AX register is our accumulator register, and like we talked about last time, it's divided into two 8-bit halves. So it's a 16-bit register in and of itself, with the left half of it being AH, which is 8 bits, the right half being AL, which is 8 bits. All right, so if we need to use 8-bit registers for something, we can access sub-portions of AX through AL. Make sense? At least at the high level what I'm talking about. Once we get into it, so right now we just got the new toolkit from Home Depot. All right, we opened it up, we see just a whole bunch of crap there. We're trying to figure out what each thing is for. We haven't actually started solving problems with it yet. We're just figuring out what they are. All right, so you know, we'll only talk about some of these things in here, so forget about the generate shortest machine code. That has to do with where it's located relative to the core of the processor. Now, all of these things, so remember when we talk about loops in Java, we talk about for loops and while loops and do while loops, and we say that each of those loops kind of lend themselves to a certain kind of problem. Remember that? It's like for loops lend themselves to counting problems. While loops lend themselves to problems where we don't know how many times we need to iterate. Well, each of these registers lend themselves to certain kinds of problems for a different reason. It's kind of the built-in way that we were meant to talk to the 8086 processor relies on these registers being used in certain ways, okay, even though physically they're identical to each other. All right, so this guy is, if you're going to store a single number, it must be, well, if you're going to store a single number, you either have to take up the entire 16-bit register, or you take up the lower half, the 8-bit register. Why is that? So let's think about that from a how this actually works perspective. New, oh, I'm not creating new, I'm opening an existing. All right, so here's our thing from last class, and really we've just taken EAX off. All right, so that guy has disappeared on us. So now this is our actual world for 8086. All right, which is still works today. It's just we're working with the 16-bit CPU world instead of 32 or 64. All right. So what that section says is if you're going to store a whole number, remember this guy is 16 bits here. This guy is 8 bits. This guy is 8 bits. So it's saying if you want to hold a full number, you either need to store it in AX or you store it in AL, not in AH. So if you want to store a number that you're going to use for doing addition or something like that, you either store it in AX or you store it in AL. Why is that? There's a mathematical reason for it, not just because they said so. What do binary numbers look like? What's the number 5 in 16-bit binary? Well, it's 1, 0, 1, right? And then 13 zeros, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There is the 16-bit version of 5. Make sense? What's the 8-bit version of 5? One, 0, 1, and then 1, 2, 3, 4, 5. AL. AX. Make sense? So if you're doing math with the numbers, using the 8-bit register says you're only going to use the second half, the low portion of the AX register. But if we had stored this guy over here and then had zeros in the other one, because that would be the default position for it, like this, it's a much bigger number, right? This is the ones place, 2s, 4s, 8s, 16s, 32s, 64s, 128s, 256, 512, 1024. So this is 1024 plus 256. That's 1280. So instead of the number 5, that's the number 1280.
So wait, you said you either keep it in AX, so it's the entire thing up there, or you keep it just in AL like that.
Yep.
So then AH is then filled up with zeros, or could you put something else there? Could you put another?
You wouldn't want to put something else in there because when it actually goes and does math, well, actually, I'm lying. Okay. I'm partially lying. The default position would be zeros, and we're going to see that when we look at the emulator. If you were doing math, if you were doing 8-bit math, okay, where your source and destination registers were both 8-bit registers, it would only look at the low half. If you're doing 16-bit, using 16-bit registers with like the add operation, then it's going to look at the entire AX. That is, it's going to look at AH and AL. So if you had put your giant number over here in AH, and this guy was over here in AL, you would have problems.
That's up to us. The computer doesn't do that on it by itself based on what your number is. You tell it to do 8-bit.
By itself, if you do an arithmetic operation like add on 8-bit registers, it will assume the value is in the lower half. If you do it on 16-bit registers, it just assumes it's that, the whole register, the whole thing. Okay? So understand that we are looking at the exact same thing here. All right? This is all the bits that belong to AX. These are the bits, well, let's flip these around here. These are those same bits visually split between AH and AL. Make sense? But they're the same bits. It's not like AH and AL are separate places on the CPU. They're just the first and second half of AX. All right? Okay, so these guys are used for multiplication, division, input and output. So, and we've kind of seen that through some of our examples, Hello World and stuff like that, where things get, where the operating system tends to want to load things or look for things. Okay? So then we have, so this guy is typically referred to as the accumulator register. All right, AX, that's what the A stands for. BX, the base address register. Now when I say base address, what does that mean to you as computer scientists? When would we use base addresses? You want a hint? How about arrays? How are base addresses used in arrays?
Because it's contiguous memory.
Okay, so that's a fancy word. What does it mean to be contiguous?
Right in a row.
Right in a row. Okay, so when we create an array, a bunch of memory is allocated, right? So if we look at this from a Java perspective, if I say int array AR is equal to a new int array 5, like that, 5 places in memory are created. 5 little buckets in memory are created for me. And those guys are going to look something like, let's shrink this down a little bit. By the way, at our lunch meeting today, Dr. Locklear advertised you as a volleyball player. I corrected him as a soccer player. Seems like you would be an extremely short volleyball player.
I used to play volleyball.
But like, are volleyball players, aren't they usually tall?
I played just the defense, so
There's defensive specialists as well.
Oh, okay, so the people by the net,
Yes.
the spikers.
yeah, they're tall.
Okay, they're tall. I gotcha. Or bad at it. One of the two. Is that? Oh yeah, you're like a volleyball pro. Are you really as good as Emo?
Me and Brian are pretty close.
So you're like pretty good, or is he not as good as he sounds?
No, I'm just pretty good.
Oh.
A lot of people don't know.
Oh, I gotcha. You're kind of short for volleyball too. Can you spike it?
I can go.
You can spike? Man, I'm like almost as tall as the net. I probably can just barely spike. Like with the right timing. So I don't have that great of ups. I can't imagine.
Gravity doesn't have to be one vertical.
I used to be able to dunk in high school. Yeah, well, I was 6'5". That was a good athlete. Oh, I used to play close to professional tennis.
I know you did tennis, but you played.
Well, but I was a good athlete. Then I broke my back and got fat. So I can't dunk anymore.
I don't have an excuse. I got stuck in a tire.
All right. So in any case, we have our base address here. When we create an array in Java like this, something that looks kind of like this in our mind gets created. Okay? And, you know, if we're thinking about this in terms of indexing, we would say this is bucket 0, this is bucket 1, bucket 2, bucket 3, bucket 4. All right? But the reality is when I say AR, if I do something like this, AR at bucket 2, what that actually says is go to AR and add to it 2 times the size of our type here, which is integer. Okay? Remember this from Java class? Some of you, well, we would have talked about this in 200 as well. Okay, so that's what's actually happening here. Well, what is AR? Well, AR is a variable. What value does AR hold? It holds a memory address, i.e. it holds the base address of this array. So if we say that, let's move these guys down here. Okay, if we say this is 100, and this is 104, you'll be able to see them in a second. 108, 112, 116, something like that. Our base address for this array is the address, the first element, which would be address 100, for example. Okay? And everything else is an offset from that base address. So the very first integer, the integer at bucket 0, lives at address 100. The next address would be address 104, assuming the base address was 100. I picked that number so we would have easy counting. Then 108, 112, 116. What does that tell us about the size of int? How big is an integer in this example? Why am I jumping by 4s? I go from 100 to 104 to 108 to 112 to 116. I'm jumping by 4s. All right, so we had somebody who should know better say 4 bits. Too busy with the Netflix stuff. 3 bits? You're just making that up now too? Here, I'll ask the question.
Usually I guess. 90% of the time I say something.
Okay, I'll ask the question differently in a way that you might get it right. What's the size of an integer in Java?
Oh, just an int?
Yeah, size of an int in Java. It's not 3 or 4 bits. Both of those are.
16 bits?
That's at least a more reasonable answer. That's a short.
That's a short. 32.
32 bits. Okay.
Yeah, 32.
How many bits are in a byte? 8. So what's 32 divided by 8?
You're asking way too much, man. I can't keep
4. 4.
That's
It's
what
4.
I said originally.
No, you said 4 bits.
No.
These are 4 bytes. These are 4 byte jump. They're not. You know they're not the same thing, right? They're different things. A bit is a single 0 or 1. A byte is a collection of 8 bits. All right. So if we wanted to, so typically we're addressing in terms of bytes, and actually realistically we're addressing in terms of hexadecimal positions. Okay. So we're keeping this with decimal numbers for us because that's easier for human beings to work with. So if our base address is 100 and we're working with Java style integers, which are 32 bits or 4 bytes big, 4 times 8 is 32. All right. So in that case, 32 bits is a synonym for 4 bytes. Our steps are 4 bytes big. First integer would be at the base address. Second integer would be 4 bytes later, 4 bytes later, 4 bytes later, so on and so forth. That make sense? So how do we resolve something like this in Java? AR at bucket 2 says go to the base address of AR, which is 100, add to that 2 times 4 for bytes. So that's 8. So that is memory address 108, which is where bucket 2 lives. Make sense? All right, so arrays would be an example of where base addresses come in. When we think about working at the actual hardware level, sometimes we need to store the base address of something so that we can work with offsets off of that. All right, as an example, if we have 10 instructions that we're giving to our CPU, and we're dealing with a 16-bit CPU, so each instruction is 16 bits, the instruction space is 16 bits, let's say. When we load that program into memory, so one of your homework assignment questions dealt with like how do we actually go from writing assembly to getting it to run on a computer, right? I think it was like 1.4 or something like that. You had 1.1 through 1.4 and then 1.15 or something that dealt with throughput of multiprocessor stuff. Okay, So one of the first ones were fairly easy, and then the last one made you think a little bit. Should have been kind of the premise.
That's what we're
You didn't even do the homework, did you?
Yes, this was last class.
Yeah, that was not for today. This
Oh, well, but you did the homework.
yeah, for sure.
Are you lying?
What? Is it not submitted? And
No, your answers don't seem to be compatible.
I'm just dumber than.
They don't seem to be compatible. Somebody did their homework.
Because I got one 4-bit versus byte question.
See,
mark.
your buddy right next to you, Zeman's like, he's like, no, it doesn't. It doesn't seem like it. And these were people who were nominated for Student of the Month.
And I guess that's why we didn't win.
Really low standards. All right. I'm not done making fun of you today, but we'll come back shortly. Okay, so when you have 10 instructions we're going to load in, those get loaded into memory somewhere. Okay, probably our system memory in preparation to move on to the CPU. All right, so we need to have the base address in memory where the next instruction lives. And then we have a program counter that tells us where we are offset from that base address for our next instruction. That makes sense? So if we assume every instruction is 16 bytes or 16 bits big, or 2 bytes in size for an 8086, that means that if we're on instruction 5, we can jump at an offset of 5 times 2, so 10 off the base address. Think of it just like an array. So if we have 5 instructions, and each of these buckets can hold a 16-bit instruction, and our program started right here, that's line 0 of our program lives at offset 0 off the base address. Line 1 lives at offset, actually these would be 100, 102, 104, jumps of 2 bytes. Okay? This would be a 32-bit CPU example for what I'm talking about right now. All right, so our first instruction lives here. Our second instruction lives 16 bits over, 16 bits over, 16 bits over, 16 bits over. Now, when you write software, don't we sometimes skip instructions? Don't you sometimes have if statements that say, only if this is true, do this crap? Otherwise, keep going. Jump over that. So we're going to have something in assembly called jump. Let's just jump over portions of stuff. So it's possible that the next instruction might be at offset 4 from the base address. And because of whatever that instruction is, the next instruction after that might be at offset 17 or 18. We might jump down the line, skipping over a bunch of instructions. That make sense? All right, so those instructions get processed by whoever's delivering those instructions to the actual CPU. And they need to grab them from somewhere, because if we have programs of various sizes, we can't rely on our entire program living in the CPU, and even if you put some reasonable size cache in the CPU, it might not be able to hold very large programs. So we're reliant on loading our program from disk, from hard drive, into system memory, your 4 or 8 gigabytes of RAM in your computer, which have a lot of space. So now they're stored in a big area where they can hold a lot of stuff that's pretty fast compared to our hard drive, but not as fast as these memory locations on our CPU. So in order to load the next instruction, we grab the next instruction based on the current program counter, offset from the base address of our program, into our CPU and have the guy start crunching. That makes sense? And we actually do something that we'll talk about later in the semester called pipelining to try to keep the CPU as busy as close to 100% of the time as possible. So there aren't these delays where the CPU is done and has to wait for you to go fetch an instruction, then load an instruction, then try to execute the instruction. We kind of want, while current one's executing, we want the next one to already be loaded and just ready to go. All right, make sense? So that's where base addresses come in. A couple of examples of how we use base addresses. So when we deal with computers, a lot of times we remember where the beginning of something is, and then how far from that do we need to travel to get to the thing we're actually interested in. Because we can address that with 2 things, correct? We can use 2 registers to get to any destination in that world. Where do I start, and how far do I have to run from that position? It's pretty handy, isn't it? We can go anywhere in memory by just having 2 hardware registers hold values. Okay? It allows us to mathematically calculate that position in memory, which means what? When we load a program into memory, what does that mean about how that program actually gets loaded into memory? The fancy word was already said today. Contiguous. Must be loaded into memory in a contiguous fashion, otherwise we won't be able to get from point A to point B. Now, in some older examples, and we'll see some of these, we can dictate what the base address is. Otherwise, the base address is given to us, relocatable memory. What's the problem? If we have a program that we're going to load into RAM, we might say, well, it's nice and convenient for us to put that at memory address 100 as human beings. That's good numbers for us to count off of, right? As opposed to having the address that it got loaded in returned to us. What's the advantage and disadvantage of both of those? When would we want to, or when would it be okay for us to choose the base address of our program?
We know exactly what will happen for sure. I guess.
Okay, what do you mean by that?
Exactly what I said. When we know.
Exactly, I basically mean nothing by what I just said. Those are words. They're great words, the best
I
words.
got the best words. Nobody else has words.
What's the risk? Let's look at this from this direction. If I try to take my program and put it at memory address 100, what's the risk?
It gets overwritten by something else.
Or something else was already there that I just overwrote, right? I'm basically throwing darts blind. Okay? So when would it be okay for me to put something at memory address 100? Don't overthink it.
When you want it overwritten,
Or,
You know it's empty.
you know it's empty. And when would you know it's empty by default?
Nothing else is running.
You're on a computer that only has one program. You're working with a system that can only run one application at a time. I know where my application lives, right at the beginning. Right? That's how early operating systems worked. So how many of you are in the 350 class right now? I hear the first quiz didn't go so hot. Sounds like some people need to read the book a little better.
Well,
That not the case?
I'd add to that.
Huh?
I mean, it's like 50 pages per chapter, and it's a lot of information.
And you didn't memorize all of it?
No.
Oh no, he's not teaching 350 this year.
No, Professor Locklear is. I'd rather do this stuff anyways.
Do you used to teach 350?
Yeah, this is the first time I have it.
Are you serious?
Why? He's a good teacher.
Yeah, but I have a feeling I probably would have done a little bit better on the quiz if you assigned it.
Well, that says more about me giving too easy. The quizzes are too easy.
Don't stop. No, we're not talking about this. No. I'm not talking about.
So I need to increase the difficulty of my
I
quizzes.
cry every time I take a quiz from you. Every time.
It's completely unexpected.
That's not what I meant, though.
That's-
I meant more
That's
like
what she
that-
said.
She wants
No,
harder quizzes. I know.
I meant more that you would have given more reasonable content to memorize for the quiz instead of saying memorize 50 pages of this really illegible textbook.
Well, possibly. I would have been more of a moving target. So I would either given you more reasonable things to target, or I would have given you a reading assignment and then quizzed you over something that wasn't in that. Equal chances either way.
I can see that.
Every semester, last semester I had a doozy. Last semester in the systems programming class, I gave an assignment.
It was impossible.
Yeah, it was an impossible assignment. It wasn't impossible. We proved in class that it wasn't impossible. It was improbable. So
You never
to
actually.
do this assignment, you needed, well, we talked about the solution. It would have worked. To do this assignment, you needed to know 5 things. Okay, we covered 3 of them. And then gave the assignment, assuming you could have solved it with those 3. I got a lot of entertainment out of it, but
Texting you show up for weeks.
there were protests, but yeah. So basically, there's an equal chance that I'm going to quiz you over something I didn't even cover, whether I thought I covered it or just couldn't come up with a better quiz question. It's all a preparation thing. Yeah, at least I'm being honest. All right, that's still cooking. All right, so what was I saying? Oh, base address. When is it okay? So early operating systems. So we go back to the early days of operating systems. So we'll take DOS as an example. And there were operating systems before DOS, but DOS was a single program operating system. Really, DOS ran two operating. On your computer running DOS, so let's say it's an 8086 computer or a 286 computer running DOS. There were two things that could run on your computer at one time. What were the two things? So you're running a 286 computer or an 8086 computer, and you have DOS on there as your operating system. And that's a physical computer. We're talking about the computer aspect of it here in front of us. What are the two things that can run on there at one time? There's one that's always running. The OS. Okay, DOS. Okay, DOS is running. Right? Now, in a situation like that where we know the operating system is loaded, could we have a hard-coded value of knowing exactly where the operating system must be loaded, and therefore we know that all the rest is for us, and zero risk, we're not going to overwrite something, unless it's from the last program we're no longer running, then who cares, right? So single user operating systems gave us that flexibility, but also cost us what? What's the flip side? What do we lose?
The ability to have it be much faster because.
Well, forget about the much faster. We'll just look at my web browser here real quick. I have a lot of tabs open. All right, and I have a lot of programs open on the computer at one time. Most of us are pretty used to that, right? Where we have multiple applications open at the exact same time. In the early days of operating systems, that wasn't a thing. You had one program loaded. Two, really, because the operating system and then the one program the user was using. Does that make sense? Simpler day. So we had our limitation. We couldn't run more than one thing at once, but also programming for that was easier because we were protected. We didn't have to worry about destroying areas of memory that might be used by somebody else. We had protected memory where the operating system lives. That was just a no-no. Okay, stay away from this chunk of memory. The rest of it is yours. Okay, do whatever you want here. Well, now in multi-programmed operating systems, in our world today, we're taking the exact same base hardware, right? Fine, we have more memory today. Back in the 286 days, you might have had 32 or 64K of memory, as opposed to 8 gigabytes of memory today, right? So our memory's bigger, but our programs are also larger today. But today we have a much harder problem. When we want to load a program into memory, we got to find a spot for it. We can't just throw it at whatever address we want and just hope for the best. Got enough memory, it might work out okay. Sometimes. Or you might overwrite some important application that just starts crashing. All right, so we need additional information. So there's additional overhead. Okay, and that's something you guys looked at in the last question from your homework assignment that you said was due on Tuesday. All right, so I got to grade that, is what you're saying. Did I grade it? I don't think I graded that one yet. In here, yeah. All right, I'll grade that this afternoon. So I think it was 1.15, which was talking about performance of multi-core processors, and there's overhead for schedule. You don't get twice the performance because there's bookkeeping that has to happen in order to say, how can I use both of these at once? How can I do two things at one time? Well, we're seeing that at the software level when we're talking about the operating system. It's harder. That make sense? All right, so we're going to be dealing with things at a fairly low level, at a very low level, literally speaking, but also we're going to be looking at it from the perspective of we're not competing with other programs because we want to really understand how does a program interact with the hardware. Not so much how do multiple kids play at the park without fighting. You know, we're not going to be solving that problem. Where we have the full use of the playground set of the park, all just for us. By the way, you know, cops will stop you in a park if you're too big for the playground equipment and you still climb on it. I am. I told my wife I would fit in that slide.
Fireman.
And she was right. Those tube slides, they are smaller than they look.
They're public parks, though. What on earth did he tell you?
Told me to get out of the slide. And I said, give me a minute. This is why my wife is sometimes uncomfortable taking me out in public.
For that one?
No. Yeah, that was another park incident, yeah. Good thing, I mean, the funny thing is some of my stories, you just can't make these up.
Well, the ones in the bathroom, I don't know why you would want to make those up.
Hey, look, everybody's got a bathroom story. Okay, so in any case, this idea of base addresses, do we kind of get the premise of it? Know where something begins so that we can deal with offsets from that for all sorts of different problems. Whether it's where does our program live, where is bucket 7 of our array, you know, where is instruction 34 of our program, all sorts of stuff. This idea of base addresses is kind of a consistent idea. That hasn't moved, has it? Hasn't that been sitting at 92.6% for like a while? Oh, like 10 minutes ago? Yeah. All right, well, we'll keep cooking. It does work because I've done it in my office, but there was a timeout, so I wonder if that's that same timeout. All right, so let's go back here. All right, so again, BX is physically the exact same thing as AX. They're both 16-bit memory locations on the CPU, but it lends itself to base address type stuff. That's kind of what the architecture says, put base address stuff here. All right, CX, the count register. And notice these guys are all divided into a high and low, play by the same rules. So count register, iterative code segments using the loop instruction. All right, so when you want to have your equivalent of a for loop and you need a counter, you put it in CX. All right, and the loop instruction specifically modifies and checks CX. It also checks something called the 0 flag. Okay, just leave it for that right now. DX, the data register. DX, AX concatenated into 32-bit register for multiplication and division. This is, remember, this predates 32-bit operating or 32-bit processors, 32-bit architectures that had a 32-bit system. So what they're saying is that in for some multiplication and division operations, which are more complex, they would concatenate those two things together to give you more bit space to work. Okay, at a high level make some sense right now, without going too deep into what does more bit space ultimately get us for those. I guess the idea would be this. Wouldn't you agree that when you do multiplications, numbers get bigger faster? Kind of a thing, right? So sometimes we might run out of 16 bits quicker doing multiplication stuff than we would doing addition or subtraction stuff. So we give ourselves more bit space. Okay, SI, the source index register, can be used for pointer addressing of data, used as source in some string processing instructions, offset address relative to DS. This last one's for very specific instructions, so don't even worry about that right now. All right, so this gives us another register that we can use for pointing to places, and sometimes that's relative to offsets, offset addresses. Destination index, DI. When I say index, what does index typically mean to you?
Start or a counter.
A number, a counter, a position in, bucket I of or bucket 7 of an array would be index 7. So it tells us where in a data structure we currently live. So when you hear index, we want to think about the position of something. Okay? So destination index register, again, pointer stuff, whatever. Base pointer, BP, primarily used to access parameters passed via the stack. Okay, so we haven't talked about, well, I think I've talked about the stack at the high level. We really haven't talked about it in here. I've mentioned the stack in here, haven't I? Yeah. Okay. And I think you probably, did you read about the stack? I think that's chapter 2. I don't think you've read about the stack yet. Okay, so the idea is that we've already recognized that we have a limited number of registers available to us. Well, therefore, it would probably be beneficial for us to have some sort of extra memory level thingy that allows us to put stuff temporarily while we overwrite things in our registers so that we can go back to where we were before, put stuff back, right? So this is kind of our, take this stuff, copy it, do new stuff here, we're done, bring this stuff back. Okay, that's where the stack comes into play. Okay, stack pointer tells us where the top of the stack is. So if you're if you've taken the 350 or the 300 course, and you deal with the stack data structures, you know, we keep track of where the top of the stack is, the front of that linked list that represents the stack. That's what SP is. Where is the current top of the stack? Okay, then we have the segment registers. CS points at the segment containing the current program. All right, so this is the segment of memory. So a few minutes ago, we were kind of referencing how we look at where our program is loaded into memory relative to a base address. Okay, so this guy would be the base address of the current program. DS generally points at a segment where variables are defined. So this would be the data segment. And we saw that in our sample Hello World program, even though that was for a 32-bit architecture, because we saw EAX and those guys. You know, we had a data section, so this tells us where that data section lives. Again, off of a base address of system RAM for that guy. So variables, you know, we have hardware variables that are our registers, AX, BX, CX, DX, those guys. But then we have made up variable names, you know, my string, length, stuff like that. And those guys actually live in system memory where we have a lot more elbow room, right? So we get to name those ourselves. And what are we trading off? When we put something in system memory, what's the trade-off? It's speed. Most of the time, the answer in here is going to be speed or heat. One of the two. Okay, in this case, it's speed. If you put something in system memory, even though it's fast compared to your hard drive, it's way slower than your registers. All right, so keep that in mind. I mean, you know, it's hard for us to pay that much attention to that stuff today as programmers because we're so used to the tool that we use, our computers being very fast, right? Even those of you who perceive your computer as slower than it should be, if you had to use a computer from, you know, the 1980s, you'd have a whole different perception of what slow means. Okay, so we're lucky that our computers are so fast today that we don't have to worry about this stuff. But we're also unlucky because we don't have to worry about it. We don't worry about it, and we end up not learning about it. Does that make sense? So there's things that are happening under the hood that we can solve problems completely inefficiently, and who cares? Computer's fast. It'll make up for my crappy programming. That's fine most of the time. But we're going to be more interested in, you know, let's say some level of efficiency at the assembly level language, and it's forced upon us because we do have a limited number of resources with which to work. All right, so DS will point to where in system memory our data section lives, where our variables are stored relative to the current program that's running. ES is an extra segment register. We can just decide how we're going to use it. General purpose registers are how they're usually called too. SS points at the segment containing the stack. So where in memory does the stack actually live? Think of the stack as a single named collection of variables. So we can have individual variables, like my string, length, hello, whatever. Those are individual named variables that will live at different places in memory relative to the base address of DS, stored in DS. So DS points to where it begins, where those guys begin in RAM. Whereas our stack lives somewhere in RAM, but we don't have to name our variables that go into the stack. We just have to know their meaning. If I put something at the top of the stack, I have to kind of remember as the programmer that, oh, I put the previous value of AX at the top of the stack. So if I want to put it back, I need to remember to pop off the stack back into AX to get me that value back. But it was up to us to remember that that's what that value was. It wasn't labeled in any way. Okay. We also have some cool shortcut stack operations that will pop all the registers, or push all the registers onto the stack and pop all the registers off the stack. So if you want to quickly kind of reset the system registers, but in a recoverable way, let's say you've been doing a whole bunch of operations that change the values of things, and then all of a sudden you decide, okay, well, I need to do something else, and I don't want to be too meticulous about, well, which registers do I have to save versus which registers do I not have to save. You can just say, push everything onto the stack. Then all the registers now are safe, including flags. You can push the flags, which we haven't talked about here yet. But then you can start making any changes you want to those registers. Then when you're done, you can pop everything off the stack back into their registers with one instruction. All right, kind of makes it convenient to do that type of stuff. Okay. Then we have some special purpose registers. The instruction pointer, we already referenced this guy, always points to the next instruction to be executed, offset address relative to CS. What was CS? Points at the segment containing the current program. Base address in memory, where the current program lives. Then instruction pointer is an offset off of that to where the next instruction lives. Make sense? Kind of seeing how these things are starting to line up. So when you look at the title of this course, it's Computer Organization and Architecture. We're kind of talking about the organization portion here. How do we keep track of where things live? Base address and offset from that base address is a go-to move in our computers. It seems to be pretty, so it's free type. Where was free type in this list? Oh, it was like number 3?
Wouldn't have aired out then.
Well, you would think it's probably still. All right, so we'll let it start. See, so there's your evidence that what I said earlier is true. It picked up where it left off because it already had the previous guys installed. Yeah, it's probably something with our network being not allowing it to go through or something, but whatever. Let it keep cooking. All right, so now we have these things called flags. Now flags we cannot directly manipulate a flag. That's mostly true. You cannot directly manipulate a flag, that's true. You can manipulate flags by taking advantage of other instructions whose result is to change a flag. But in general, flags give us information about what just occurred. So we might run a command. So for instance, the comparison command that compares two values to each other. And then the result of that, depending on which flags get set, tell us which number was less than or greater than the other one, that kind of stuff. So different flags get set for different situations. So if you want to think about your flags as basically being a whole bunch of lights, and those lights have some meaning. And the flags, just like our registers, all have names, and they're usually used for that reason. Like a flag that gets used very often is the ZF flag, which is the 0 flag, as well as the carry flag, the CF flag. So those two are pretty commonly used. A lot of the other ones are general purpose, isn't fair to say, but they're not part of our general cadence. They're one of those things that every once in a blue moon, these guys come into play and that kind of stuff. But flags are a way of giving us bit-based information, on or off, was the current value of CX 0. So when CX becomes 0, the 0 flag becomes a 1. That's a way of testing whether CX is 0. Except the 0 flag is 1, for example. Okay? So we have a big list of flags. So we have the carry flag. This flag is set to 1 when there is an unsigned overflow. So, for example, when you add 255, which is our largest byte, correct? So 8 bits, so it would be 8 ones, comes out to binary, or comes out to decimal 255. If we add 1 to that, now we're at 256. 256 does not fit inside of a 8-bit number. Therefore, our number becomes 0 across the board as you do the math, as you add 1 to it. And then we have, let's look at that here. So it's kind of an important concept that we're going to bump into. So if we have 111, that is the number 255, right? So that's 128 plus 64 plus 32, 16, 8, 4, 2, 1. It's going to give us 255. When we add 1 to that, the answer should become a 256, which will require 9 bits to hold. Make sense? 256 would be 1 followed by 8 zeros. That's 256. Well, we might be storing this inside of AL or AH, and those guys can hold 8 bits. It's like, look, I get you want to hold something that takes 9 bits. Can't happen. I don't have space for that. I have 8 bits for you to work with. So if we try to add 1 to this guy, I'm going to steal this here. So 1 plus 1 is, let's give our answer down here on the bottom too. That just gives me my spacing. They're not going to be all zeros. So 1 plus 1, well, they will actually be all zeros, but I'm going to replace them. 1 plus 1 is what? Well, in decimal, that's 2. 2 is not a number that exists in binary, right? Our numbers, our digits are 0 and 1. Our bits are 0 and 1. So 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. 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 CF. Make sense? Carry flag will get set to 1. It can only be 1 or 0. It's a bit size flag. And when it's a 1, that means that the last operation you did had a carry. Therefore, there's a pretty good chance, as in there's a very good chance if you were doing math, that the last thing you were doing, the value you're looking for, isn't all there. A huge, big chunk of it's there, but the rest of it's over here. you got to keep going. That make sense? All right. So that's where carry flag comes into play. Okay, parity flag. This flag is set to 1 when there is an even number of 1 bits in a result, and to 0 when there is an odd number of 1 bits. Even if the result is a word, only 8 lower bits are analyzed. So a word would be 16. So a word is 2 bytes. A double word is 4 bytes. So this guy, parity flag, basically tells us, is the number of ones even or odd? If that might be helpful to us for some problem. All right, and one thing to keep in mind for something like that is you're not always doing math. you might use the elements of a binary number to keep track of something other than the mathematical equivalent of that number. So if you have 8 switches on a wall, so we're going to keep it with an 8-bit thing. Okay, so we have 8 light switches on a wall. And only the first 2 switches are on and the last switch is on. The number might be 1, 1, followed by 5 zeros, followed by 1. We don't care that it translates into some big decimal number. Okay? It's not important to us. What's important to us is that we can keep track of which switches are on and which switches are off. So now we're using that binary, those 8 bits for representative data rather than value-based data. Make some sense? Okay. Auxiliary flag set to 1 when there is an unsigned overflow for low nibble. And here is your 4 bits. There you go. So nibbles. So a half a byte is something called a nibble. A half a byte is something called a nibble. So we have 4 bits, and this guy says that when there's an overflow for the low 4 bits of this would be for a byte register. So if you think of AX as subdivided into AH, AL, think of AL as being not directly subdivided into 2 nibbles, but there are 2 nibbles that make up AL. So this gives us information about the lower 4 bits in AL. That makes sense? So if we're doing math based on those nibbles, this tells us whether there was a carry relative to that nibble. All right, 0 flag set to 1 when the result is 0. For non-zero, result flag is set to 0. So 0 flag is a 1 if we have a 0 in the result. And the result is usually going to be in, let's say, CX for right now. That changes, but let's just say it's CX. All right. Well, actually, let me give some clarity to that. When we say the result, typically we check flags after we perform an operation. So, for example, if we do a comparison, I mentioned a few minutes ago that we have a command that lets us compare 2 values. Shouldn't come as a surprise, right? Kind of like an if statement. You know, if this is true, do something else. Jump somewhere else. I referenced jumping earlier. Okay, well, we referenced jumping in a couple different contexts as it relates to this and also my inability to do so. But, you know, the punchline here is that usually you would issue a command and then you would check the flags. So we would presume that many commands have an impact on the flag. So when we say the result, what we're really talking about is the result of the previous command that was executed. Whatever that guy did. Usually the result is going to deal with whatever the destination register was for a command. We kind of looked last time and saw that most commands are command name, destination, source. Some of them are a little bit different than that, but for the most part, let's say that's the case. If destination is where the answer ultimately will live, if you check the flags right after a command, if the 0 flag is on, that means the value of that destination is currently 0. Make sense? All right, so that's what they mean by the result. The result of the previous thing you did. So that comes down to understanding what each of those tools does. If we think of each of our commands that we're going to learn about as a tool that we get from Home Depot, each one is going to say, after this is done, here are the flags that I will change. They don't always all change all flags. Okay, I think I mentioned a few minutes ago the 2 big ones that are used often are the carry flag and the 0 flag. Those are common flags that many commands change. But we'll have to learn that about the tool. We'll have to look at the command and say, okay, well, the result of this can be experienced in multiple ways. I could look at the destination register, but I can also look at whatever flags that command manipulated to figure out what the result of the command was. Make sense? All right, sign flag set to 1 when the result is negative, 0 when it's positive. So, this pretty much the same thing I just said, except this tells us something about whether it's a positive or negative number, and that's going to relate to something called 2's complement, which we'll talk about next class. Trap flag, used for on-chip debugging. So this is a thing where they, you hook wires up to the chip and you're trying to stop things. So think of it almost like a break point. If you've used a debugger before, okay, you can trap an instruction and then analyze what's going on. We're going to be faking that using this 8086 emulator, so we can actually see what things look like. Interrupt flag. This flag is set to 1. CPU reacts to interrupts from external devices. So this is whether or not the CPU is in a mode where it can be interrupted. When would we want to have the CPU in a mode when it can't be interrupted? People who have had the operating systems class already should have the answer to this. When would we want the CPU to be in a mode where it cannot be interrupted? See, you're going to be better off in the operating system class with somebody else. I mean, these nothing. They retain nothing.
I know it. I'm just not gonna give it fun. When it's performing,
And man, you might get it right. I actually think you're.
wait. It's one CPU cycle for what's it called?
Yeah. Okay. You're right.
There's a word for it that I'm not gonna remember. Atomic. Yes. I love this man. Atomic.
That was your main competition. You're just a fan of his because you both lost.
Yeah, exactly.
Okay. Yeah. So an atomic operation, something that occurs as if it happened in one CPU cycle. So here's our evidence of what happens if something can't actually occur in one CPU cycle, but we still want to make the CPU non-interruptible. We do an instruction that sets this flag. Don't allow the CPU to be interruptible, to be interrupted. Make sense? For those of you who are taking 350 now, you'll learn about atomic instructions. They're important. Sometimes you need something to happen in a way that nothing else can race in there. We talk about McDonald's in that example when I teach the class. Where 2 people rush into McDonald's and both try to grab the cash register at the same time. It would be bad if they both could place their order at the identical time. So sometimes things need to, there's race conditions and we need to be able to handle those. All right, direction flag. This flag is used when some instructions to process data chains. When this flag is set to 0, the processing is done forward. When the flag is set to 1, the processing is done backwards. I have no idea when you would ever use that. I guess with whatever some instructions are. I can't think of an example of an instruction that would use that. So if one pops up, I'll let you know. And then the overhaul flag. This guy's actually fairly common as well. Less common than the carry flag and the 0 flag, but common as well. So set to 1 when there is a signed overflow as opposed to an unsigned overflow. For example, when you add 100 plus 50, result is not in the range of -128 to +127 when we're dealing with signed numbers as opposed to unsigned numbers. So we would get an overflow in that particular case. That makes some sense? All right, so homework assignment. First of all is get your emulator working using the thing I already have up on Blackboard. And then from chapter 2, let's read sections. I'm going to give you enough. Let's do 2.1 to 2.3. So just these 3 sections. And then I'm going to give you, I won't actually give you exercises from the end of this chapter because I don't think any of them do what I want you to do. I'm going to give you a couple of commands for you to run in your emulator and then give me screenshots to submit. All right, showing me your emulator's working and, move this value into AX and what does the emulator show you? Go ahead.
They're going to kill me, but you signed up to 2.6.
That's fine. That's fine. You're still going to use the emulator. So if you've already read that, that's fine.
Oh.
Don't read anymore. If you're already up through 2.6, that's fine. All right, so I'll put up the assignment for what to do with the emulator. So get the emulator working, and then I want you to use the emulator for the assignment. All right?